All right, welcome to Chapter 7, Section 2, Transformation of Initial Value Problem. So this is the next section in using LaPlace transforms. So at the end of this online lecture, a student should be able to find a LaPlace transform for a derivative. Also should be able to find the LaPlace transform, use LaPlace transforms to solve differential equations. Should know how to find Laplace transforms of functions that look like t times the exponential function to the at power and t times sine of kt. And they also should know how to find Laplace transform and inverse Laplace transforms of integrals. So let's get started. So we have been solving differential equations of this form. So we have linear, non-homogeneous, nth order differential equations with constant coefficients. And in order to solve these, we have needed initial conditions to help us find some functions. So here are our initial conditions. Evaluating, the first one evaluates the solution itself at t equals 0 and it's equal to some constant, and then you have the derivative evaluated at t equals 0 equal to another constant, so on and so forth, until we have enough initial conditions to help us solve the differential equation. So if we have an nth ordered differential equation, we would have to have initial conditions all the way up to the nth minus 1 derivative to help us solve it. And the intent of this lecture is to show you how to solve these using Laplace transforms. So the idea will be like this. You'll take the Laplace transform of this differential equation, and applying properties of Laplace transforms, we can rewrite it this way. So if you have the Laplace transform of the sum of two functions, we can write it as the sum of the Laplace transforms of these individual functions. And then you can also factor out coefficients that are multiplied times these functions out in front of the Laplace transforms. And so you would get an equation that looks like this. Our problem is we don't know how to find the Laplace transform of this function or any derivative. So today we will learn to find Laplace transforms of derivatives. So how do you find the Laplace transform of derivative? Well, you apply theorem 1 here. And if we have a valid function we can take the Laplace transform of, you find the Laplace transform of the derivative by finding the Laplace transform of the function itself, multiplying it by s, and then subtracting off the initial value of that function, evaluated at t equals 0. So how will we apply it? So let's look at this one. Let's say I wanted to find the Laplace transform of the second derivative. What I need to do is apply the Laplace transform information. So I can write the second derivative as a function of a first derivative. So if we do that, applying the definition of the derivative of Laplace transform, I take s and I multiply it by, in this case, the Laplace transform of the first derivative. Because this is the second derivative, I have to go down in order of 1, and then subtract off the initial value of the derivative of that function. Well, what is the Laplace transform of a derivative? Well, that's the one we just talked about. That is s times the Laplace transform of the function itself minus its initial value. That means the Laplace transform of that is equal, the Laplace transform of the first derivative is equal to this. Now you multiply through by your s, and you get this expression, the Laplace transform for a second derivative. All right, so, and then you can plug in replace the Laplace transform of x of t and write it in terms of Laplace space, a capital X of S. So this is the Laplace transform of the second derivative. And if you wanted to find higher order derivatives, we can do the same thing we just did there for the second order. And we repeat it until we get down to our Laplace transform of our solution function that we want. In this case, this representation, we're trying to solve for f of t. All right, let's look at an application. So we want to solve this differential equation right here. First thing I do is I take the Laplace transform of both sides, applying properties of the Laplace transforms I have as sum of two functions, and I can split that up into the Laplace transform, the sum of the Laplace transforms of those two functions. And then I'll factor out the 4 because it's a constant, and I have to find the Laplace transform of these. The cosine of t is quite straightforward. It's right in the table. You can look it up. And then the Laplace transform of x is just capital X of t right here, or capital X of s, times 4. And then this is the Laplace transform of our second derivative using the method I just showed you earlier. So now, well, I got to figure out what the values of these x at t equals 0 and x prime at t equals 0. Well, we come up here and they're claiming that they're 0. So if we plug in zeros for those, our solution goes to this, and now I can solve for my x of t's, x of s's here, and I factor out the s's, and now I can solve for my x of s's, and I get this. Now, if you try to find the inverse Laplace transform of this function right here does not show up in the inverse Laplace, or in the Laplace transform table that I handed out. What you have to do is put it in a form to make it look like that. And the form we're going to use is something called partial fractions. So the idea is this. I have a denominator here. It's made up of these two functions. And if I write it this way and add those two functions together, or add these two fractions together, I should be able to produce this. This is a partial fraction technique. Now, since I have s squareds on the bottom here, I have to have a polynomial of order of s one less than what I have on the bottom. So a polynomial in s of a linear polynomial, in this case, to the power of 1. So I've created some constants, a, b, c, and d. They're just constants. And I need to find out what values a, b, c, and d need to be so that I can turn this sum of fractions to be equivalent to this fractions. So the way we do that is to find a common denominator. And the way I have to do that is I have to take as plus b and multiply it by s squared plus 1, and then take my s and my cs plus d and multiply it by s squared plus 4. Now if I multiply that out, I get this, and then I want to group together common terms. So I got s cubes there, I got s cubes there, I got s squareds here, I got ds squareds here, I got s's here, and I got constants, a constant b here and a constant 4d there. Okay? Now, if I can group those together with these terms. Now the trick now is my denominator is the same as what the first fraction I started with right here. So what I have to do is figure out what all these constants have to be, a, b, c, and d, in order to make the numerator here equal to the numerator here, which is just the case of s. So to do that, I look at the coefficient in front of s cubed, right there, a plus c, but I see no s cubes here, so a plus c has to equal 0. I look at my coefficient right here in front of the s squares and my b plus d, but I have no s squareds here, so b plus d has to equal 0. I look at my coefficient here, a plus 4c times my s's. Ooh, I have a coefficient here in front of my s. That coefficient is 1, right? So a plus 4c has to equal 1. And then I have my coefficient here, my constants, d plus 4b, sorry, b plus 4d, and I don't see anything over here that has a constant. Well, that has to be 0 also. So now I have my 4 equations. I also have 4 unknowns, a, b, c, or d, so I should be able to solve this. So let's start solving it. So this first equation tells me that a has to be equal to minus c, and if I plug that, and then also that my b has to be equal to minus d. Now if I plug them in to my equations down here, I should get, since a is equal to minus c, I can plug it in for a down here, and I can solve for c. So 3c has to equal 1, and then c has to equal 1/3, so a has to equal minus 1/3. Do the same with b, so minus d plus 4d has to equal 0, or 3d has to equal 0, so d has to equal 0. That means b has to equal 0. So now I have my 4 constants, a, b, c, and d, and I can plug them back in. So I have my c, my a, my d, and my b, and if we plug them back into our representation of our function that we started with originally, I get this expression. Now I can take my Laplace transform, inverse Laplace transform, I should say. So I take the inverse Laplace transform of this, using properties of inverse Laplace transforms. I can take the sum of 2 functions and turn it into the Laplace transform of the 2 functions and add them together. I can factor out my coefficients. Now I have this function, inverse Laplace transform of these 2 functions, which show up in the table. This one should be cosine 2t, and this one should be cosine of t. So our solution for this differential equation is a minus 1/3 cosine 2t plus 1/3 cosine t. Let's practice this again. So I want to find the solution to this differential equation. So I take the Laplace transforms of both sides. I use properties of Laplace transforms and write it this way, and now I got to find the Laplace transform for the second derivative, and that should be equivalent to s squared times x of s minus s times x evaluated at 0 minus the second derivative of x evaluated at 0. And this gives us a Laplace transform of x, and this Laplace transform of cosine of 3t is equivalent to s divided by s squared plus 9. And we can get that from the Laplace transform table. So I need to find my initial conditions here. I find them right up here. They're given to us. Remember, you can't use Laplace transform without having initial conditions. So I find out that x at evaluated at t equals 0 is equal to 1, and its derivative is 0. So if we plug those 2 in there, I get this expression. So now I want to put everything with capital X of s on one side, everything with just s on the other. And if I get this expression if I do that. Now I can factor out my capital X's of X's, my capital X functions, or my Laplace transform functions. And now I can solve for my Laplace transform function. And if I do that, I get this expression. Now again, this will show up in the inverse Laplace transform table, or the Laplace transform table. This will not. So what I want to do is find a common denominator. And that's what I get. And so I need to find the inverse Laplace transform of this. This will not show up in the Laplace transform table, so I got to represent it to look like it shows up in the Laplace transform table, and that's using partial fractions. Since I can take the denominator here and represent the product of two functions, which is a fraction, I can represent that fraction this way if I know these constants A, B, C, and D. Now again, to do partial fractions, I'm a value s squared, so I've got a function on top of it that's of one order less than s squared, which is s, so it's a generic polynomial of a linear form of s on both. Okay, so I have to make this fraction, okay, I have to make my right-hand side, I'm claiming it's equal to my left-hand side. But they don't look that equal right now because I don't see the same common denominator here that I see here. So let's make my right-hand side look more like my left-hand side. To do that, I have to do the common denominator. So my s squared plus 1s I have to multiply by my s squareds plus 9s, and my s squared plus 9s I have to multiply by my s squareds plus 1s, and now I have the same common denominator on both fractions. So I can add these fractions together and do some algebra. Cross multiply these, and if I do that, I get these expressions. So now what we want to do is group together all the same terms of powers of s's. So I got a power of s cubed there, s cubed there, powers of s squared there, powers of s squared there. I got powers of s here. I got a power of s here. And then I have a constant here, and I have a constant here. So what I want to do is group them together. And if I do that, I get this polynomial associated with this fraction, and this is the polynomial that has to equal it to make those left-hand side and right-hand sides equal. So let's look at this. I have an s cubed here, and I have an s cubed here. A power that has a power 1, so a plus c has to equal 1. I have an s squared here, but no s squared over here, so b plus d has to equal 0. I have a s here, and I do have an s here, so 9a plus c has to equal 10. And then I have two constants over here, but I have no constants over here. So 9b plus d has to equal 0. So I have my four equations and four unknowns, a, b, c, and d. So I should be able to solve this. So let's try and solve it. I think the b plus d equals 0 one's easier to solve, so this gives me b is equal to minus d, and if I plug it into my 9b plus d equation on the bottom, I will get d equals 0. So I'll get a minus 9d here plus a d, that's minus 8d. And that has to equal 0, so that's going to force d equals 0. So d equals 0. That forces b to equal 0. So 2 of my coefficients are done. Now I got to find my a's and my c's. Now the way I'm going to do that is I have a c here and a c here. So here's what I want to do. I'm going to take this equation and subtract this equation from that. So I've got 9a minus a. That gives me 8a. I have c minus c. That's 0c. No c here. And I have 10 minus 1. That's 9c. So this is going to give me a is equal to 9/8. So if I take this a, and I plug it back into this a over here, that gives me 9/8 plus c equals 1. And now if I solve for c, I get a negative 1/8. So now I have all my coefficients. I plug them back in to the initial partial fraction I started with. So if I do that, I plug in all my values, I get this value for my Laplace transform. So now I can take an inverse Laplace transform of both sides, applying properties of inverse Laplace transform. If I want to take the inverse Laplace transform of the sum of two functions, I can write it as the inverse Laplace transform of the individual functions summed together, and then I can factor out my coefficients. And so now this function shows up in Laplace transform table, and this function shows up in Laplace transform table. And we can find them. If we look them up, we find that our solution to this differential equation is going to be 9/8 times cosine of t minus 1/8 cosine of 3t. All right, let's practice this one more time. Let's find the solution to this differential equation using Laplace transforms. So I have to take the Laplace transform of both sides, applying properties of Laplace transforms. Then I have the sum of two functions. I can write that as the individual Laplace transforms of the sum of those two functions. I'm going to factor out my 9, and so I have to find the Laplace transforms of these individual functions. Well, 1 shows up in the Laplace transform table. It's 1 over s. The Laplace transform of x is just capital X of t times 9. And now I've also got the Laplace transform of my second derivative right here. And by using the definition that we talked about earlier. So now what I have to do is find the Laplace transform of, I got to find the value of my initial conditions, x of 0 and the derivative of x evaluated 0. And if we come up here, we find that there's 0. So I can write my problem this way. Now I can factor out my capital X's of S's like this, and I can solve for what capital X of S are. Again, I don't think this is going to show up in the Laplace transform table yet. So what I have to do is write it out in partial fraction form. This is a little bit different than what we did earlier. See, this fraction does not have an s squared, so this is an order 1 linear polynomial, so I write a generic polynomial 1 order less. In this case, it's just a constant. And this is the same thing we've done before. Since this is of order s squared, I can write it of order 1 order of polynomial less than that. So bs plus c, a generic polynomial. And now I got to find the common denominator of this to make these two functions look similar. Well, they are equal already, but I want to make them look better. So I got to find my common denominator, and that's what I'm going to do. I'm going to multiply by two factors of 1, but they're different factors of 1. This factor of 1 over here is s squared plus 9, and this factor of 1 is just an s. So I got s over s and s squared plus 9 over an s squared plus 9. Now I have the same common denominator, so I can add those fractions together. And then I'm going to group my terms like I did before. So I grouped all my s squareds together, I grouped all my s's together, and I grouped all my coefficients together. So now I have the same common denominator as I had up here. So this value 1 has to be equal to the same value here. And this is what's going to help me find my coefficient. So if I look at that, my constant up here is 1. My constant down here is 9a. So 9a has to equal 1, or a has to equal 1/9. Again, I have no powers of s. I have a power of s down here, but no power of s up here. So my c has to equal 0. And then I have a power of s squared down here, but no power of s squared up here. So a plus b has to equal 0. All right, so let's solve this. I already know that a is equal to 1/9. I also know that b has to be equal to a minus a. So b has to be equal to a minus 1/9. And I also know that c is 0. So if I take them and plug them back into my equations up here, I will get a form that shows up nicer in the LaPlace transform table. So again, I got to find x of t. To do that, I got to find the inverse Laplace transform of both sides. Applying properties of Laplace transforms, it comes down to this. This shows up in the Laplace transform table. That's equal to 1. This shows up in the Laplace transform table. That's equal to the cosine of 3t. So my solution to my differential equation is this. We get 1/9 minus 1/9 cosine of 3t. All right, almost done for today. I got to show you the definition of how to find the Laplace transform of t times an exponential function to the at. And there's two ways we can do this. The first way is this one. I can use this representation that shows up in the Laplace transform table, where I got my two e of t functions here, right? And then my f of t in this case is equal to t. So the inverse Laplace transform function I'm looking for has to be t, so I have to find that first. So the inverse Laplace transform of t is equal to 1 over s. Now what this tells me is everywhere I see an s, I have to replace it with s minus a. So if I do that, I can get the inverse of the Laplace transform of this function, and it should be 1 over s minus a squared. All right, so that's way number 1 to find the inverse Laplace transform, or Laplace transform of this function. The other one is this method down here, where here the t's are the same, but my f of t function is different. So according to this, I have to find the derivative of my Laplace transform. So I need to find my Laplace transform first, so I know what I'm taking the derivative of. So I have to find the Laplace transform e to the at. Well, that's in the Laplace transform table. That's 1 over s minus a. And now I have to take the derivative of that with respect to s. Well, you apply the quotient rule. And if we apply the quotient rule, I get a derivative that looks like this. All right, so I have to, according to my table over here, I got to multiply by this minus. So the Laplace transform of t e to the at is equal to 1 over s minus a all squared. And you'll notice that this way of finding the Laplace transform and this way of finding the Laplace transforms are the same. So we did it right. They give us the same answer no matter which Laplace transform you use. All right, one more Laplace transform, in this case t times the cosine of ct. And I'm going to use a method I showed you earlier, this one. Again, the t's are the same. So my f of t in this case now is sine of kt. So I got to find the derivative of that Laplace transform. So I have to find the Laplace transform first of sine of kt. That's equal to k divided by s squared plus k squared. And that's in the Laplace transform table. And now I need to take the derivative of that with respect to s. If I do that, I have to use the quotient rule and then also the chain rule. And if you do that, you get this derivative. And according to this table over here, I have to multiply that times a minus. So the Laplace transform of t times sine of kt is equal to this expression. All right, one last Laplace transform, and that's the Laplace transform of an integral. So let's say we have the Laplace transform of this integral, right? Where we have a function we're taking the integral of, right? Now, according to theorem 2, to find the Laplace transform of this integral, what I have to do is find the Laplace transform of this function first, and then multiply it by 1 over s. So it's equivalent to this Laplace transform. And if we do that, there's also an inverse Laplace transform. So if I see a Laplace transform, or if I take an inverse Laplace transform of this function, and I can write it as that function times 1 over s, then its inverse Laplace transform would be this integral. All right, so I hope you have a better understanding of how to find the Laplace transform of a derivative, how to solve a differential equation using Laplace transforms, how to find the Laplace transforms of these two new functions, t times the exponential function to the at power, and t times sine of kt. And I also hope you have a better idea of how to find the Laplace transform and an inverse Laplace transform of integrals. That's all I have for you today. I'll see you in class. Bye.